Hello, maths and physics fans.
Yes.
Someone's very excited about this. We are back doing another maths versus physics collaboration. This is Zhelyo from Z Physics, and we did part one about a year ago now, where you challenged me to the physics admissions test, the PAT, which is the exam you take if you want to apply to do physics undergraduate at Oxford, which of course is where we are. And then I threw back at you the maths admissions test.
Which was really hard.
Yes, and the physics one was also pretty tough as well, right? Like,
I hope you brought something easier today, but...
Well, no, you're in charge of this. Sorry, so no, this is all
It's
Zhelyo.
true, yeah.
Right, so...
It's my doing.
He has promised me something harder than an Oxford admissions test on the theme of maths versus physics. So what are we doing?
We're doing the International Physics Olympiad, probably the hardest physics competition that you can find. But what I actually found was a question that I think you would absolutely ace. The question is essentially on fluid mechanics, the Bernoulli equation, which is something that you probably teach as well.
I do. Okay,
Yeah.
I like all of these things you're saying. I didn't like International Physics Olympiad. That sounded scary, but I like fluids, I like Bernoulli. Okay.
And we combine all of these into essentially the fascinating world of chimney physics. Who knew?
Chimney physics, all right? Yeah, I know nothing of chimneys, but I know fluids and I know Bernoulli. Okay.
It's a really fascinating problem because it's not only appeared on the International Physics Olympiad, it's also appeared on the JEE Advanced Exam in India, and it's also appeared as an undergraduate problem at the MIT Year 1 physics course as well, I think.
Oh,
so
wow.
there's a lot of history behind this problem.
There is a lot of history behind this problem. Okay, well that sounds fun. I'm going to try the International Physics Olympiad question. I'm going to do that one here on my channel. This is part one. And then, obviously in retaliation, I have picked an International Maths Olympiad question.
God. I've actually seen some IMO problems just for fun in the past, and I've always just kind of looked at them for about 5 minutes, and I've thought, oh my God, I could never solve these. So it'll be...
You're going to need a lot longer than 5 minutes. So the Maths Olympiad questions, you have to do 3 in 4.5 hours. Mm-hmm. So these are tough questions, but we'll save all of that. That's part 2. Mm-hmm. Part 1 is me doing physics. So you've told me about this fantastic question. So I guess... should we just get stuck into it? Do some chimney physics?
Yeah, let's do some chimney physics.
Right, a lot going on here. Nice diagram, which I always draw my own diagrams, so I'm going to clearly do that. But there is a diagram of a chimney. What else have we got? Okay, gaseous products are burning. It's giving me various variables, which are then all shown in the diagram. And a lot of assumptions. Okay, so I'm going to start. Okay, I'm going to draw my diagram. I'm going to be my go. Would you draw a diagram here as well, or would you just kind of use the one in front of you?
I'll probably use the one there in front of me, but I've also noticed that here is one of the big differences between physics and math Olympiads, where when you look at a math Olympiad, it's normally like, prove this, and here's a really simple statement within a couple of lines, where physics is like, here's a page of information over this like really interesting physics phenomena.
I was thinking there is a lot of information here, actually. Okay, so we've got width A, height H. I think the reason I like to redraw diagrams is it just makes sure that I'm like not missing any key info from the one, because I think when you look at it, you can miss sometimes what's happening. I don't know, it's a me thing. Whilst past Tom stalls for time by redrawing the very clear diagram already given in the question, I thought it might be fun to give the Physics Olympiad problem to a few different AI systems to see how they get on. And lo and behold, the results are a mixed bag. Some of the answers make a little bit of sense. Some of them are indeed pretty good, but some of them are just complete and utter nonsense. But rather than just complaining about AI systems being unable to solve difficult maths and physics problems, what we really should be doing is figuring out how to make them better. And that's where today's sponsor, Aligner, comes in. Aligner connects domain experts with frontier AI projects to help train how models think, reason, and respond. Experts across maths, coding, medicine, law, science, business, and languages are earning up to $150 per hour working on projects that are remote, flexible, and paid weekly. With such great benefits, it's no surprise that thousands apply every day, But with the industry growing at such a breakneck speed, so too is the demand for people that have the ability to reason through hard problems and apply their thinking. Regardless of your level, as long as you have the relevant experience, Aligner are keen to speak directly with people who have a genuine interest in training AI. If that sounds like you, then scan the QR code on screen to apply, or you can click the link at the top of the video description box to head direct to the application website. Now, let's head back and see if past Tom is indeed smarter than AI. Okay, so right, let's get on to the assumptions. So we've got lots of stuff happening here, and now we have various assumptions. Okay, so this is where I'm probably going to need your help as my physics cheat sheet. The velocity of the gases in the furnace is negligibly small, right? So that's just telling me they're 0, right? So V is 0 down here. Okay, fine, like that. The density does not differ from the air of the same temperature. I would have assumed that anyway. The pressure of air. Okay, hydrostatic pressure. Okay. So I know what that means, right? But do I remember the formula? Okay. So hydrostatic pressure means... Oh God, so I would say, how would I do this as a mathematician or fluid dynamicist? So I would jump in with like the Z component of Navier-Stokes here, which I totally, actually it's not how you're going to do it, but I would jump in and be like, okay, so if I'm doing a Z component, I would say dP by dZ is, we're assuming that's
Love this. Absolutely
the only
love
way
this.
the pressure changes. This is not how you would do it, is it? Equals, so it's going to be equal to the force, external force, so it's minus G times rho A, probably. I assume rho air. Okay, I think that is going to be my pressure gradient. I'm going to integrate this. I have no idea what the constants are going to be, so let's just call it...
We've got physical conditions for this, so we can probably figure it out.
Let's just call it A minus, and then these are both constants, and I'm going to put Z. Now, there's a very important question around signs. I'm not going to worry about that yet.
Okay.
Because I know I'm going to use Bernoulli's, right? You already told me I'm using Bernoulli, and I know when you do that, as long as you're consistent, things should cancel out. So we'll see. This might backfire, and you should totally not do this. But I'm just going to, like, for now, ignore directions and try and be consistent.
I'm curious to see what happens.
Mathematician's advice. Don't, right, physicists, don't listen to me. Okay, so I feel like you would have written this differently, but I'm going to say that I think that is currently sort of what's going on with my pressure for now, because I've not even finished the assumptions yet. But now it says I can use Bernoulli, right? So, and then the last bit is change of density. Okay, great. So I've done the assumptions, and I'm going to use Bernoulli. Right? What does it actually want me to do? I haven't even looked at the actual question. But I will write down Bernoulli because this is going to be important. Okay, so Bernoulli is saying, so this is actually only true on a streamline.
And what is a streamline?
A streamline is, I always think of it as like the path that would be traced out by like a particle of air.
Yeah.
But like there is a mathematical definition which I totally teach in my second year fluids course, and I've completely forgotten what the definition is. It's like you define it as like, oh God, something like dx by ds is u, or there's some like, you change coordinate systems and you can figure out exactly what it is, and there's a proper way of figuring it out. No, the velocity is everywhere parallel to a streamline.
Yeah.
Right?
I think so.
Yeah, no, you sounded convinced. I think that's it. There is a proper definition, but we're told we can just assume Bernoulli. So
all the fluids courses were actually my favorite at the university.
Good. Good, I like that. Okay, so Bernoulli is telling me, it tells me Bernoulli, doesn't it? Me trying to remember it, right? So half rho v squared. Okay, and I'll worry about what rho that is in a moment. Plus rho gz. So that's like kinetic energy plus potential energy, basically, plus pressure is constant. Yes, that's what I was expecting to be true. So I'm going to assume the question is going to ask me to use that. Yes, minimal height of the chimney. God, for it to function efficiently. I don't know what that means. We'll worry about that later. Special result in terms of all of these parameters. Okay, so the point is that h is unknown, and we have to figure out h, basically. And we're going to use pressure and density and velocity and Bernoulli. So, I know Bernoulli So this is constant. So let's evaluate it at, I'm going to call it z equals 0, but basically what I mean is inside the combustion thing, like the bit that's burning, right? What do you call it?
I don't know, the bit where Santa jumps in on Christmas. So.
No, this is not in the chimney. This is in the fire. I'm going to write brackets
well,
fire.
hopefully not.
That bit, right?
Yeah.
So that's what I mean by z equals 0. So
Okay,
down there, like at the bottom of the streamline, let's say.
They call it the furnace in there. So.
Furnace!
Yeah, that's the one.
That's the word, thank you. Okay, so in there, z equals 0, we're allowed to assume the velocity was negligible, right? So I kind of saw where this was going. So I can get rid of that term. Z is 0, so I lose the potential energy term. And so all I've got is the pressure at, let's say, 0. Pressure at 0 is now my constant, right? So that's my constant. So now I'm going to do the same at the top of the chimney, because the point is I want an equation for H. And you're nodding along as though I'm doing this correctly, so this is good. So we also then, by Bernoulli, this constant, it's the same constant for all z, so if I plug in z equals h, it's going to be the same thing. It's still p of 0. So we're in the chimney, so it's rho s. It's the smoke density. We've got v, which I possibly need to figure out. I'm not sure. We'll worry about that later. But it's no longer 0, is the point. It's moving out.
Yep.
And then it's plus rho gh, and rho again is rho s, because it's the smoke, and it's equal to my constant, plus p of z, I'll worry about that in a minute, equals p of 0, because that's my constant term. Right, and I think p of z is this thing up here. Oh God, okay. But if this is p of z, then p of 0 is just a. So I think this is just going to turn into, but then I don't think it is quite a, is it? Oh gosh. I'm a little bit worried about what's happened here now.
Yeah, so I think at P of 0, you want the pressure to be greater. So you want the additional hydrostatic term because of the differences in height, compared to the pressure just being atmospheric pressure at the moment where it sort of like leaves a streamline. So I think
because it's going to flow from high pressure to low pressure.
Exactly, yes. Which
so it has to be higher pressure inside. So am I?
And if the height h is big enough, the velocity should be sufficient for it to escape rather than build up.
So is it basically, what am I trying to say here? So the point is that this should, so this should actually be some constant reference value, let's call it b. And then I think, you're then saying it should be plus
I think
G
it should be
rho
a plus,
a h minus z.
h minus z.
Because now if I sub in z equals h, I think this is right, because when z equals h, it's just some constant value. And so b is what I'm calling atmospheric pressure, apparently. This is still true. If I differentiate this, I still satisfy my differential equation. And when z is h, I get b, and when z is 0, I have some larger value than b.
Oh, I see, yeah. So you've placed the coordinate system kind of like originating at the
We will
bottom of
not
the
worry
chimney.
about what I've done with the coordinate system. Okay, I was hoping this wouldn't come back to bite me. It kind of has. But I think that's right. That's actually what I wanted to write initially, but I wasn't sure if I could kind of jump to that. But I think that, to me, that sort of makes sense. Okay, and that makes sense to you as a physicist?
Yeah, I think as
Done in a weird way.
Yeah, I think as a physicist, I would probably just think, okay, I've got some atmospheric pressure, let's say here, plus there's going to be some added pressure from the weight of the air directly just above it, and that hydrostatic pressure is rho gh. Which is a classic little derivation.
Okay, so I've thought about it as like boundary conditions of I want P to be this random constant at z equals h.
I did not expect you to be invoking the Navier-Stokes on this, but
any opportunities? What should I say? Okay, so this now makes more sense to me because I think now what we're going to end up with, this is a very roundabout way of saying, I think we've now got a half rho s v squared. plus rho S G H. Now, I think the pressure here is at Z equals H, so it's just, so I lose that, so it's just this constant B, whatever that is, but I think it's going to cancel because P of 0 is B plus rho G A H. Right, and that's rho, not G A, rho A.
Yep.
Yeah, that's what I was just trying to be careful of. G is constant, it doesn't change with air or smoke. Rho A, G H. Okay, and then I can just ignore B, right? I knew I didn't care about that bit.
Yep.
I knew it was good. Okay, this makes more sense now because I can now, right. But I don't know H.
Well, that's what we're trying to figure out, right? So...
Well, this is going to give me a velocity.
Yep, but if we know a certain velocity, that's going to correspond to the height to that sort of velocity.
Oh, okay, right. I'm going to reread the question. The minimal height of the chimney.
Because this here is essentially your minimum condition,
Let me
isn't
tidy
it?
this up. Yeah.
Your velocity needs to be higher than this one. There was another condition that we wrote earlier as well.
Okay, so V squared is, I'm just tidying this up because there's a lot of things floating around that are annoying me, is 2 GH is a common factor, yes. And then it's rho A minus rho S divided by rho S. Okay.
So this is a really interesting result, actually, and I'm pretty sure I've got a different way of getting to the same answer without actually using any of the Bernoulli equation. Any guess what that might be?
I mean, so like, the thing I've ended up with having used Bernoulli is basically there's a kinetic energy term, obviously, in Bernoulli's equation, but then the other bit, because of what we've assumed about pressure, it's just fully turned into like potential energy.
Exactly right, yeah. So we could probably write sort of potential energy is directly equal to sort of kinetic energy. And in the fluids world, just kind of thinking of density, we can take the potential energy to...
Be my guest.
Exciting, I get to write as well. Physics. We can take the, well, let's set the potential energy to be equal to the kinetic energy.
Yep.
So we could say the difference in density, which is kind of like our equivalent of the mass in the fluids world.
Yep.
Multiply that by GH. Gosh, my handwriting is so much worse than yours. You know?
I'm used to this particular tablet.
Yeah, sure. Let's set that equal to a half density times V squared. And that here should be rho S, right? Shouldn't it? Because it's the smoke that's actually escaping.
So it's literally just that, isn't it? That's
it's just
the exact equation
that.
we've got. Oh, wow,
so
okay.
if we were to rearrange for that, I don't think this actually appears on the mark scheme.
I was about to say, like, would you be okay, like...
I think as long as you as long as you solve using the correct method, I kind of like just need to finish writing that because otherwise it will bug me. Rho S GH
divided by the rho S.
Divided by rho S.
Yeah.
But as long as you reach the correct method, it really shouldn't matter which road you take.
We would hope.
Yeah.
You would hope you would have that freedom. I would hope you have that freedom in something like an Olympiad.
Oh, for sure.
Versus, you know, like a school exam where it's a bit more rigid.
Oh,
annoyingly.
yeah, for sure.
So you would hope so. Like, as long as you're doing sensible things, well explained. Okay, yeah, cool. I mean, I just saw Bernoulli and was like, and you told me it was going to be Bernoulli, which is fine. I like Bernoulli. Okay, so anyway, I don't think I've actually solved it, have I? Because I've got...
What is the problem actually asking? Because they give us some variables that they want the answer in terms of, right? Because they want the height of the chimney.
I know,
H,
and that's...
In terms of like some stuff. In terms of B, whatever that was.
Yeah, so B was a volume. So I think I can already see where they were going with that, to be honest, because I think the idea is this could be used to give me the velocity, but then what do we know? Oh, okay. But then there is, so you've got like a production. I know it's probably not called a production rate, but I'm calling it a production rate, which was like B, right, which was a volume per time. So you're
Yep.
producing some amount of gas, and it's leaving through cross-section A.
Yeah.
So it's telling you the velocity it has to leave out.
Yeah. Yeah. Yeah.
Right, so it's, so its reduction rate is B. The area, let's call it the exit area.
It's a constant area, isn't it?
Is equal to A, the cross-section area. So obviously that much must flow out at this speed, otherwise it's just not working, right? Like it's not being efficient. So you're saying then that V must be greater than or equal to B over A, basically, right? Because if it's not, then it's not being efficient. If V is smaller than that, then you're producing more than is allowed to escape. So it's just going to like build up, and it's going to be terrible. Not only would that be not efficient, that feels like it's dangerous if you're not releasing the gas that's produced. Okay, so V has to be bigger than, so now I can make that an inequality up here, can't I? I'm assuming. So that tells me that V squared must be greater than or equal to B over A, but we know what that is. So that thing is greater than or equal to B over A. Oh God, so 2 rho A minus rho S G H over rho S. That must be greater than or equal to B over A squared. Whoops. B over A squared.
I did the same thing the first time I saw the question, actually.
Right.
Allegedly.
And now I can rearrange this for H.
Yeah.
So H, but this doesn't look like the answer they want, but I'm going to just go with it anyway. So they wanted the minimal height. So the minimal height is when equal. So min when equal. Right, so H must be equal to B squared over A squared. We got a 2G, so 1 over 2G. And then rho S divided by what I would call rho delta, but I'll write it as rho A minus rho S. Okay. And that is going to be my height, which is not how they want it.
There's a bit of a problem with that. Imagine that you're designing a chimney, and then, or somebody wants to build a chimney. Probably they're not going to want to care too much about the relative density between the outside air and the inside conditions. They probably might want to look at temperature. Hey, outside is going to be minus. Let's have it a bit warmer. Outside is going to be 5 degrees. Inside is going to be like 25 degrees, you know. So we want to focus on sort of measurable, useful quantities. Not that density is not useful, but, you know.
I knew this was coming. And this is why I was like, initially when it started talking temperature, I'm like, this is such a physics problem. Like this is the answer. Yeah. However, the question wants it in terms of temperatures. So I've got B and A. I've obviously got G. So what I think I need to do, and I have no idea how to do this, so you're going to help me. What I need to do is there is a way to turn this into temperature.
Yeah, there is indeed.
Okay, so is this to do with, I think there was an assumption I may have skipped over, possibly on purpose, who knows, earlier that mentioned, where did it say something? The gases can be treated as ideal.
Exactly. So one of the things that I tell my students is, as soon as they see things like that, is just to like immediately write down the ideal gas law equation.
All right. Well, what is the ideal gas law equation? My physics cheat sheet over here.
So it's PV, where V stands for volume, not velocity.
Yep.
Is equal to nRT.
I have seen this before. Okay. Yeah.
So N and R just let's assume that they're just constants in this case.
Yep.
And one of the things, so how would you link velocity, sorry, how would you link volume?
So V is volume, right?
Yeah,
I'm just gonna make a note of that.
With potentially with density. So.
Oh God, well, it leaves you with a mass, right? When you
multiply them.
exactly.
Yeah. So because density is mass over volume, we could probably say that volume is mass over density. And now suddenly you're gonna have a link between density on one side and temperature on the other side, which you're gonna which you can then use to express the minimal height of the chimney.
So they're inverses of each other. Is that
exactly,
what we're arguing? Because it's a ratio. Okay.
There is something slightly controversial in this problem, though, which you'll probably
because I can say Sorry, I'm just getting very excited because I think I figured this out. Okay, so once I've got this, so volume basically looks like 1 over density.
Yeah.
Right, so I'm just going to write this 1 over rho. So because I've got rho divided by delta rho, all of the constants are going to go, aren't they?
Yeah.
Like the P, the N, the R, because of this ratio thing. Right. So if rho over delta rho then must look like delta T over T. Would that be right? Because they are inverses of each other.
Yep, exactly right.
Yes. Okay, good. So does that mean I can now Oh God, so I've got T over delta T. What does it want it in terms of? That, right? T air. But would it be T air on the... but I've got that as smoke. What are you doing to me?
Yeah, this is one of the bits where we have to be quite careful with the indices. One way to look at it is I tend to include quite a lot of steps with my working out. So I would have probably just gone P sort of mass over the density is equal to nRT.
Okay, yeah. I'm gonna have to be more careful.
Yeah.
Okay, right.
You probably have it right, but the indices can get quite confusing.
Mass
at least for me.
divided by rho is n times r times t.
And then I'll probably put all the constants onto sort of one side, and then see if I can get some sort of proportionality relationship.
Okay, so P times m for mass divided by nr times 1 over density is equal to t. So as I said, t looks like a 1 over rho. So, it's just the way around that they've written that's just annoying me. Could I actually, because I think I've basically got this, could I just say this is, if I divide through by rho s, could I do it that way and say this is 1 over rho a over rho s minus 1? Because then, oh God, what's that?
So one of the things that I would do kind of like on this side is just go 1 over rho t has to be equal to some sort of a constant, because assuming that, and this is a little bit contentious by the way, but assuming the pressure is a constant, m is a constant, n is a constant, r is definitely a constant. So 1 over a rho t is a constant, so that means that rho 1 t1 has to be equal to rho 2 t2 if between the 2 points.
Okay.
So that's going to say that's going to give you a direct relationship between sort of rho a, because if you bring the t over here on this side, you're going to have 1 over rho a.
So 1 over rho a ta
has to be equal to
1 over rho sts.
Which means that rho a ta has to be equal to rho sts, which means that you're in business now.
We think. Okay, so rho s over rho a.
You're on for that gold medal.
It's ta over t. It's ta over ts, so they flip. Yeah. I'm happy with that. So that's what.
We just need to flip them now.
So that's what's going to change up here, then, isn't it? So because I've got rho a over rho s, that's now ts over ta. God, this is such a complicated way when I basically had the answer. Physics. Okay. And then I can multiply through again by TA if I want, and it's now TA, is it over delta TA? Better bloody be. Yes, okay, good. Over delta T. Okay, so I think I've got it. So I think, just to neaten it all up, I think the answer to part A, part A of D.
That's the hardest part,
I hope
for sure,
so,
I think.
is that the minimum height is B squared over A squared, 1 over 2 times gravity, and then we got that to be TA over delta T. Right, that better be correct.
One of the things that I always tell students when they're dealing with such problems as well, and I'm sure you do the same, is just to, so if you're in an exam, if you're in a competition, I would just say, just check the unit, see if this thing is dimensionally correct right at the end.
Even I tell my students this, yeah, no, that's a good idea. So obviously the temperatures cancel out, don't care. 1 over gravity, 1 over an acceleration, and then b squared, that was a velocity squared.
Yeah.
Okay, so I've got an L squared over T squared, and then I've got a 1 over
the area.
1 over T squared over L.
So it does.
So it's an L.
So it's an L.
Yeah. Yay! Okay, good. Right, dimensionally correct. I'm happy. I mean, the bit I was less sure about was like the A and the S was confusing me a bit.
Yeah.
But appreciate the physics
pleasure,
cheat sheet over here. Okay. Right, let's get on with this. How long did I have to do this question, by the way?
So in the IPHO, you get 3 different problems for a total of 5 hours. So it will depend on
Oh,
how
wow,
you
okay.
do. So it's, even though there is definitely a major time component, you do probably have a little bit more time to think compared to, let's say, something like the
Well, that
ESAT,
feels
for
quite
instance.
generous. Like you've just said there, that's like a good hour and a half.
Some of these
plus.
problems are totally horrendous, though, I have to say. And just, I think probably the hardest part is actually starting them for a lot of the problems. So especially some of the harder parts, just putting something pen to paper to try and...
You helped me by being like Manui, and then even though we've realised I could have done it without. But...
Yeah.
Okay, right. Part B. So this is much fewer points, only 0.5 points compared to 3.5. Why not use whole numbers physics? Come on. Okay. Two chimneys are built to serve the same purpose. Cross sections are identical. Okay, interesting. Designed to work just temperatures, blah blah blah. Oh god. The height of the chimney designed to work in cold regions is 100. How high is the other? Right. Okay, so I'm thinking, let's go. The information I've got is the cold region. Okay, so cold, I can say the height is 100. We know this. I do not know B and A. That's fine, but they're going to be constant because they're not going to change. Gravity doesn't change, but temperature does change. So then I know that this and this is all one big old constant, which I'm going to call alpha, because that's just not going to change. And then it's equal to the atmospheric temperature minus 30. I feel like I'm going to need to use different units, but I'm going to write minus 30 degrees C. Don't worry about that in a minute. I know I'm going to have to use Kelvin, aren't I?
Yeah.
Because you don't want to use...
I think
feel
it's
like
just
negatives are not...
It's a good idea. You don't want to get PV and RT is equal to 0 and get some stuff which is really unphysical.
Yeah,
so
okay.
I just use Kelvin by default.
I don't know much physics, but I know I know you
Good.
should always use Kelvin. As
Fantastic,
I do know that. I do know that. Right, but anyway, I'm going to write it for that now.
Sorry to interrupt, but where's the square on your t-shirt? E is equal to MC. Is there a square?
We're not going to... No comment. No comment. I didn't make the t-shirt. In fact, you picked that moment to mention this. Right, and then I'm dividing by... The furnace temperature is 400, but it's not 400, it's the delta T, so that's 430. Because the difference between the furnace temperature and the negative is 430. Right, so I now just need to turn this into Kelvin.
So the 430 will just be, because delta T is delta T in whichever units you're dealing with, right?
Good point.
Yeah, so we don't have to worry about that.
Well, that's if I know how...
Well,
so,
unless you're dealing with Fahrenheit, because I've lived for a year in America, and I still have no idea how to convert to Fahrenheit. Sorry, people.
So Kelvin, you literally just add a constant.
Yeah, 273.
Okay, thank you. I was about to say, I don't know the constant, but there we go, okay.
Absolute 0.
Right, so in Kelvin then, right, okay, cool. So in K, the equation I have is 100 equals alpha, we don't care about alpha, times 243 Kelvin over, I mean, I'll do it properly. Oh no, the delta doesn't change, you're right. The delta, of course, doesn't change, yes. Yeah, it doesn't change. Perfect. Okay, so I think that's true in the cold region. So in theory, that now gives me alpha, right? And then in the hot region, I don't know H. I've still got alpha, so I can just write it. And then I'm told the new temperature is 30 degrees C. So 30 degrees C is 303 Kelvin. And then divided by the delta. So 30 to 400 is 370. So I think it's that where that's alpha. So I therefore think that H, if I've done this correct, is equal to alpha, but alpha is 100 times 430 over 243. So that's alpha. Does that make sense? Possibly. Multiplied by 303 over 370.
We might have to use a calculator.
I think I am going to have to use a calculator. Are you allowed?
Yeah, we are.
Oh, you are? Okay, okay. I mean...
This is not the International Maths Olympiad. You can use a calculator.
Okay, what do I think this is approximately? Does this make sense? I want to make sure this makes sense.
Yep.
So that's like 30 out of 37, which is basically... Oh, that's like... it's like 30 out of 36, which is like 10 out of 12. So it's like 5/6. So I think that's about 5/6. And then this one, I just want to make sure I haven't got a very silly answer, but I think this is okay. Because I expect this to be taller. right? It should be
Yeah.
taller because the temperature difference is smaller, and that's on the bottom. Yeah, okay. I think that makes sense. Yes, wait.
Yeah, I think it does.
You have a taller chimney in the hot area.
Because
Interesting.
the temperature difference is smaller to the furnace, assuming
Yeah. So it doesn't. But then why do you have a taller chimney?
I'm gonna have to like travel around to like some warmer
I
regions
know,
around the world and
because
just
that,
compare
like,
chimneys.
The equations work. Yeah. Okay. Yeah.
I wonder if there's some sort of a linear dependence from the equator to a North Pole.
Okay, and then that's like 430 over 240. Oh God, what's that? It's like some kind of number. Let's just suppose
I'm a physicist. I just use a calculator.
I know. It's not how we work here.
Yeah.
It's 42, approximately 42 over 25. Okay, this is very approximate. So I think this is approximately 100 times 42 divided by 6 is 7 times 7 divided by 5.
That's amazing.
Okay, so 700 divided by 5. 140-ish. Okay, I think it's about 140.
I think the actual answer was actually 145. So this is very impressive. I'm pretty sure it was.
Yes, a win for not using calculators.
Shall we just see? Yeah, 145 exactly.
We've got 145 on here's the one I did earlier. Okay, well, 140 is close enough. And that's it. Okay, good.
Awesome. Really, really good.
Yeah, let's keep it moving. Okay, how does the velocity of the gases vary along the height of the chimney? Make a sketch or diagram showing the cross section does not change with height, indicating the point where the gases enter the chimney. What?
I think for a physicist, this problem will be quite counterintuitive, but for somebody like you as a fluids person, I think you will probably be able to tell the answer almost instantly.
Well, yeah, because it's constant.
Because it's constant, yeah.
Yeah,
exactly.
we made an assumption.
What are we even talking about? Yeah.
Okay. So yeah, V is just equal to, I mean, there's lots of ways to write it, but we had it as A over B. It's just constant, right? Because it was the minimum. Okay, so the velocity is constant, but I'm assuming here what this question is trying to get me to think about is all of these assumptions, because we had it as 0 in the furnace, and it's like jumping up to this constant value, right? So if I were to do like a sketch or a plot, I think what's happening here, and this is over the height. Yes, how does it vary? Okay, so let's write, this is velocity, and then this is height, weirdly the wrong way around, but so you're starting at 0, and then we just like enter the chimney, and then it just jumps up to a constant.
Yep.
It's just that, right?
Totally physical jump. Yeah.
We could use a hyperbolic tangent function if you want. I mean, that's what we use for jumps.
So that'll be a really cool video, actually, probably. But
all right, and is that all I had to do, really? How does it vary?
I think so, yeah. How many points was that? Was that 0.5?
Yeah.
Well, that one's 0.6.
Honestly, these scales, just multiply everything by 10 and everyone's happy.
I think it's actually from historical reasons, because the first IPHO had 6 marks per question, so they decided to keep to the original.
Okay, fine. Fine. Okay, last one. How does the pressure vary along the height? Ooh, okay. Oh, okay, this is... So we assumed hydrostatic pressure in the air, and we assume that there's like a constant pressure in the bottom bit. So we can just use Bernoulli, right? Because I said, so if I have a general, at general Z, because I worked out the constant was just P of 0, whatever that was. But then at general Z, we would have a half rho S V squared. We know V because it's constant. Plus the rho S G Z, because we're now at some height Z, plus the pressure at Z equals P of 0. So I think that's how the pressure varies. Because this is constant. This is the key thing. This is constant and equals A squared over B squared. There's lots of ways of writing it, but ultimately we assumed it was that, didn't we? So that tells me then that P of Z is just P of 0 minus rho GZ, so it's decreasing as we go up, right? Plus a half rho s a squared over. I think this a squared over b squared, this, if I remember from earlier, could be turned into something involving density and gravity. But like, who really cares? Because the point is...
If we were to sketch it, it's going to be a linear
it's a
relationship.
linear, yeah, it's literally, this is just linearly decreasing. So if I'm going to attempt to sketch this, just to complete the question, we've got... Okay, so this again, my x-axis is the height, just to confuse everybody.
He's so into the physics. I love it. I knew that you would like this problem.
I do like this problem. I'm just happy because I've basically finished it. But at the beginning, I was like, I'm not happy about the temperature density. Like, I had the answer in density, guys. Come on. So the pressure, I don't know. So the pressure is something initially.
I agree.
Okay, so there is some value, and then you like enter the chimney, and there's going to be like a little bit of a weird jump there, I think, possibly. I'm not sure, but then it's just going to linearly decrease, right? It's definitely just decreasing, and it's going to be some other constant value later on. Like, I think.
Out of curiosity, why do you think the little jump potentially happens?
Because it doesn't really make sense, right? Because we've got a jump in the velocity.
Yeah.
So I feel like just from Bernoulli, that has to be counteracted by a jump in the pressure, doesn't it? Possibly, right?
I think so.
Yeah. Because you're sort of saying Z hasn't changed, right? Because what Bernoulli basically says is, like, how I think about it is it's sort of like, approximately, velocity plus height. It's PE, but I think of it as height. It's the only thing that varies. Plus pressure is constant. So if we're saying we're going to assume that these sort of, the furnace-y bit has like negligible height, like you're sort of going from 0 to epsilon if you want, right?
Yeah.
So that's not changing. So if the velocity is jumping up, the pressure has to jump down, I think. I don't know, I might be overcomplicating it, but I think it starts at a value.
It's really interesting because...
It jumps and then... I think what it's after is there's a linear decrease, because it says how does it vary along the height of the chimney, which is the linear decrease. But I'm thinking because the velocity, we've established the velocity is jumping up, I feel my intuition says there should be a jump decrease in the pressure. Don't know. Just a thought.
It's super interesting. But yeah, this completes the first part
does?
of the IPHO. Yeah, well done. Absolutely. It's super interesting to see how the way that you would have approached these problems. And yeah, thank you so much for having me here. I really appreciate it.
No, I honestly really enjoyed that. I mean, hopefully everyone watching could tell. That was super fun.
My job is complete.
Yeah, like if I just sort of like, I'll give you my recap of my thoughts. So like, obviously fluids. Love that it was fluids. I'm assuming this is all pretty correct, right?
Yeah.
Okay, good. I just want to clarify that.
I'm pretty sure, actually, yeah.
Can we do like an audience direct?
Yeah.
Like, I want this for the audience.
Yeah.
Can you just please confirm to the audience that I just got all of the physics correct?
He absolutely smashed it. In a good way. Yeah.
Yes. Okay, good. Just for my ego. Now my ego is satisfied.
You're officially a physicist.
I mean, it was a fluids problem, wasn't it? We'll kind of not talk about my choice of axes on the pressure. I felt like that was going to mess up, so I appreciate your like little hint and nudge to make me think about that. And then it was subbing in, and then I like your little nudge about energy. It felt like it was actually just energy balance. Okay, then I figured out the H. I'm dying on this hill. I'm not happy that I couldn't leave it in density. Of course, the question asked for it in temperature. I get that, but like I feel like having it written as it was. I mean, it's fine. Come on.
There's something slightly dodgy, to be honest, in the way we've used PV is equal to RT, because we've assumed that P is a constant.
Which it clearly isn't, because
so
like remove that bit, right? Leave that in terms of density.
Yeah. Viewers, what are your thoughts about this?
Yes. Rant in the comments, please.
Yeah.
Okay, because I'm not happy. I would have left it in density, but sure, we manipulated it to get what they wanted.
It's physics' fault, really. This time it is, yeah.
Okay, and then there was me refusing to use a calculator, good, which was close enough.
That was amusing.
Just the last two bits were I think they were just trying to get you to think more about the assumptions we've made. I kind of like that, actually. That to me felt like we've done some maths. Is it okay? Like I'm a mathematical modeler, so I like it when you're forced to think about the modeling you've done. because it's so easy to just assume stuff, get an answer, and just like be like, this is the answer. But when you're modeling a real situation, you should always be like you said, sanity check on units, but also like, does my answer make sense? Because like we've kind of assumed the pressure was constant, but then also that it wasn't. So like, it feels like this is not the best model, being honest.
Yeah.
I don't know, maybe this is how you model chimneys. I don't know. I
think the problem actually has some references on like chimney design that have inspired the problem. It's pretty interesting. Yeah.
There we go. Right, we can put those in the video description.
Yeah.
We'll put if anyone's interested, go read some physics publications on chimney design.
It's a fascinating read.
It is. All jokes aside, I thought that was awesome. That was just really fun. I feel like last time I was like terrified, but I appreciate your help on the...
Don't worry, I'm terrified today of the IMO, so...
Well, I was about to say, so maybe the terror is coming, right? So I mentioned this at the beginning. I have just done a question from the Physics Olympiad, and by all measures, I think I've done pretty well. I did have to use my physics cheat sheet a little bit, but I am very pleased with how that went. You're now going to try, probably against your will. The only fair question in response, we're going to try and do an International Maths Olympiad, an IMO question. So I've picked one. I won't reveal it yet because this is going to be in the second video. So if you're just watching this for the first time, go over to Z Physics, where you can now watch part 2, where Zhelyo will be trying to do the Maths Olympiad question. It involves polynomials.
Oh, God.
That's all I'm doing.
You might see me cry. See you then.
We don't know yet because you haven't tried. Maybe we will, maybe we won't. Okay, so make sure you go check that out. Make sure you also subscribe if you've enjoyed this, and also check out all the other stuff over on Z Physics and subscribe there. You know, why not just subscribe to everyone's channels, right? Let's
all the channels.
Woo! Okay, but no, thank you as always for watching. Thank you, Zhelyo, for coming to Oxford.
Thank you for having me.
Presenting me with this question. You're not going to say this after we've done the maths one next. So I'm getting you to thank me now. But no, pleasure as always. And as I hope all the viewers are, I'm very excited to see how you get on with the maths question.